Study the concepts of overfitting, generalization, underfitting, and cross-validation in machine learning. If you want to revisit a specific concept in this lecture, please look into the description where I have time-stamped specific topics. So if you are looking for a specific topic to study, please visit the description. Now let's start with the lecture. What we have studied in the previous lectures 1 and 2, we studied the linear regression and polynomial regression. And we know that the supervised machine learning algorithm is best understood by an approximating function y is equal to f of x, where your target function is f of x w, which best describes your data to predict an unknown or unseen data, taking your predictor variables or variable x as input. This characterization describes the range of classification function y of x and prediction problems and the machine learning algorithms that can address them. An important consideration in learning the target function from the training data is that how well the model generalizes to unseen or new data. Here we see that generalization is important because the data we collect is only a sample and it is incomplete and it has fluctuation. So generalization is the concept to determine how well or ML algorithm, machine learning algorithm, will predict or classify unobserved or unseen data. The data that we are training or model is incomplete. Why? Because it is only a sample and it would contain noise as well, and there would be some fluctuations. There will be some outliers in your data. So the best model is based on generalization. Generalization refers to how well the features of the data are learned, and it is a field of inductive learning. Inductive inference aims to learn the general concepts. So what is the purpose of inductive learning in general? It learns the general concepts or general patterns in your data. From specific examples. We cannot give all the examples. We give a set of examples and our model should learn the general concept or general patterns in our data, which is exactly the problem that supervised machine learning algorithm aim to solve. So this is the problem that machine learning algorithms are trying to solve, specifically supervised machine learning algorithms. They are trying to solve this, that you give the specific examples, you give a data set, and the model should learn the general concept, so that when the general concept are learned, you give unseen data, or model still can give a good prediction. So the general concepts are learned from specific examples, and when unseen data is given, it should give a good classification or good prediction. So what is overfitting? So now our model is trying to learn from specific example. It is trying to learn the general patterns in our data, so that when a new example comes or unobserved example comes, our model can still predict it with some good accuracy. Now the concepts of overfitting and underfitting, we are going to discuss those. What is overfitting? It refers to a model that learns from the training data too well. Overfitting happens when a model learns the details in the model and also the noise in the training data, to the extent that if it negatively impacts the performance on new data. So in overfitting, our model not only learns the features in our data that we want to learn, but it also learns the noise in our data. And it superfits our data such that when a new example comes or new data comes, it is not able to perform well. And it is mostly common in nonlinear or non-parametric models, where we try to solve them by using flexible learning functions. So there are some techniques they can be used to address this problem of overfitting, specifically in nonlinear non-parametric models. One of the technique that is used in decision tree is pruning. So we will discuss what is pruning in decision trees in a while. First, we develop the concepts of overfitting and underfitting and the best fit model. So these three concepts we are going to study and develop the concept, and then I will give one example of how we can address the overfitting. So overfitting is when the data is that the model learns not only from the training data, it not only learns the general concepts, the features that we want our model to learn, but also the noise in the data. So the problem is that these concepts, they do not apply to new data, and they can negatively impact the model ability to generalize. What is underfitting? The next concept is underfitting. So underfitting refers to a model that not only that is unable to learn the general features in the data, and it also performs worse for new data. So it has poor performance in learning the general concepts. Therefore, it gives a poor performance for your new data. Here we had the model was learning the general concept in the data, or the features in the data, plus the noise in the data, which led to poor performance. But in the underfitting model, the model is unable to learn not only the general concepts, but it has a poor performance. Also, it has poor performance on new data. So in crux, what we can say, our model is not learning. So what is the techniques that we can use to address these overfitting and underfitting problems? So here is a sample loss function and model fitting concepts. In the first figure, we can see that with each epoch or training iteration, epoch 1, 2, 3, 4, our model is learning from the training data, and this is your loss function. So a good learning rate is shown by this. So in the first few iterations, the model is learning quickly, a steep curve, and then it stabilizes. From this point, it is becoming stable, and from here to here, it remains nearly constant. So this is a good learning curve. However, if we look at the green curve, very steep decline, and then our data model becomes constant over here. So it is a higher learning rate. And for a low learning rate, we can see that the model is not learning that well. Loss value is not going down with iterations, with your epochs. And there is the value of loss. We can see here, for good learning rate, loss value is here. For a high learning rate, loss value is here. And for our low learning rate, our value reaches over here. And a very high learning rate is counterintuitive, in fact. Your loss function starts to rise. So in these three lines, we can see, okay, our model gets constant after certain epochs, and this is what we want to achieve. There should be a stable loss, which indicates that the model is trained. So not only we want stability, we want our loss value to be as low as can be. So a good learning rate is giving us the lowest loss value. So here the keyword is learning rate. Let's look into first what is learning rate. What is a learning rate in machine learning algorithms? So we covered some part of gradient descent in the previous lecture, lecture number 4. We studied the gradient descent algorithm, the mathematics behind it. So what we were trying to do basically was, at time t plus 1, we have an initial wt weight value, and we subtract the partial of our error function with respect to the weight values and multiply with the learning rate. So this is the learning rate. Higher the learning rate value, increases this derivative value, and a lower learning rate value would add a smaller value of this learning rate, of this derivative partial function. So in terms of graphical or visual representation, let's draw the gradient. For example, on the x-axis we have weight w, and on the y-axis we have the loss. We can say E of W also, okay? That is what we are trying to minimize, right? The error function or the residuals. So weight W, and then we have loss on the y-axis. So we are updating the weight values. This is the weight at time t. Subtract this value so we subtract this value from the existing weight value to get or up new weight value or update the weight. So in gradient descent, this is what is basically happening. The gradient is basically trying to reach this lowest loss value. We are trying to reach here. For example, this is your global minimum. Of loss. So our model will perform the best if we can reach here. So this is our gradient update. This is the WT plus 1. This is the learning rate effect. So if the value of learning rate is too small, for example, here we can see, so it will take too many iterations to reach the lowest point. But in the case of a very high learning rate, for example, initial random initialize was here, and we update the weight values. This learning rate is very high. So our value of the gradient fluctuates too much. So the learning rate is very high. It causes drastic updates in weight values, which is not suitable for the learning algorithm. So a very low value or a very high value are both not recommended. So what is the best fit model? What is the optimal learning? So optimal learning would be such a learning rate. This is the lowest point that we want to achieve for our error function, the loss function, and weight values. So the learning function, the learning rate should be such that it reaches to or minimum value of the weights for each update, WT plus 1 update. This blue line indicates a WT1 update value. We need to adjust this learning rate so that our model learns within optimal time. That is the target of the learning rate, and it is displayed here. So now we revisit the concept of learning rate here. So a good learning rate will not only reach a low value, constant value, but it will also reach to a lowest value. Now comes the overfitting and underfitting concept. So for each epoch or each iteration, this is the area where the model is not trained so well. And you can see your underfit model will start to rise. This is your training loss, the purple line. Purple is your training loss and yellow is your validation loss. So at the time of training, you train the model, and then for a specific unseen data, you test it for the validation loss. So when your loss starts to rise, that means your model has been overfit. And you can see the model is not learning that good. It should have a reduced value. So it should follow the pattern of your training loss. The ideal is that the gap between your training loss and validation loss should be minimized. The lower this value, the better your model is trained. So now comes the concept of what is training and loss and what is validation loss. We will discuss this. So we will discuss the training loss and the validation loss in the next few slides. So just hold on to that concept. Here we are trying to understand overfitting and underfitting. So which order polynomial will best fit for this data? So we already discussed this example in linear regression and polynomial regression in lecture 2, 3 and 4. We already discussed these concepts of linear regression and polynomial regression. So we want to find a best fit line for this data. So when the order of polynomial is 1, meaning your line is represented by this, where m is your slope and c is your intercept. C is the intercept value where the value of x is 0, and slope determines the direction of your gradient. So for a first order polynomial, your value is a straight line with certain slope. But if your zeroth order polynomial, that means in case of this x raised to power 0, then it just becomes 1. So m plus c. Your value is a straight line, horizontal line for order of zeroth order polynomial. So in comparison, if you can see both of them, in this case, this looks a better fit for the representation of these data points. What about if we increase the order of the polynomial? Let's suppose we increase the value of this polynomial to 9th order, x raised to power 9. Predictor variable has the power of 9. So here we can see when m is 9, all the data points are covered by the best fit line. Do you think this is best? Here the error is 0. Do you think this is the best learned model? Do you agree with this, that there is 0 error? There is no error in your function, all this function f of x perfectly defines all these points. So what is the purpose of machine learning? This is the next question. Are we trying to learn the given data as exactly as possible, or are we trying to predict the unknown data as exactly as possible based on your given data? So for 0th order polynomial, we have a horizontal line. For first order polynomial, m is 1. We have a straight line. For third degree polynomial, we have a better fitting data. And for 9th order polynomial, it best fitting or existing example, right? Because our error is 0. So is this the best model? Again, the question, which model looks the best? As we can see, with the order increase in M, the complexity of the model increases. You have to do calculations up to 9. And then we discussed in terms of matrices, the size of the matrix will increase. For each variable, we have one equation. So the total equations become W0 to W9. So we should have 10 equations in total in our matrix, and we have to solve that very complex model. As the complexity of the model increases, the model exactly learns the given data. However, the prediction accuracy does not necessarily increase. Why? Because our model is just trained for these points. So if unknown point comes, unseen data comes, where will the model have space to learn the pattern of that data? How will we be able to predict? That's the question. So no, this does not look like the best representation of the data. From these 4 examples, this looks like the best representation of our data points. So how do we select our model? We have approach to select different models. So we start with several approaches, and then we need to choose one of the model. We have several models and we choose one. Once the model is selected, we have certain level of accuracy. Then we try several different parameters of the model and need to choose one. So first you select the model among different models. Then you configure your parameters. And then you can evaluate your models based on training and testing data, or you could use the cross-validation. The first concept is you have a train and test data split, and then you have cross-validation. So for your tests, your whole data set is divided into training and testing, and then you first train the model, and then for the testing data you test the model. In cross-validation, we are going to cover in this lecture today. So here the concept of data partitioning is mentioned. What is data partitioning? When they mention training data, validation data, testing data. So these are your data partitioning, dataset partitioning. So what you're doing essentially, for example, this is your whole data set from sample 0 to 100k samples. What you do initially is you split your data into two parts. For example, we select 80% of our data is used for training your model and 20% of your data is used for testing your model. So those data samples, for example, each bar represents one data sample. So the data samples in your test data should not be present in your training data. So for testing, we have unseen data that is not used in your training. One more concept here of validation. So what is validation data? Again, your training data is further split into two parts. Among the 80k, 50k are used for training and your 30k are used for validation. And this part is your testing. So your whole data is divided into actually three parts: training, validation, and testing. So, and validation is used during your training time. So what I have mentioned here is your whole data set is partitioned into training and testing, and your training data and the second part we have is your validation.